Hi, uh, good evening, and welcome back to this problem solving session for the NPTEL course Geology and Soil Mechanics. So, today we are about to solve uh, numerical problems regarding a new topic in soil mechanics, that is shear strength of soil. And it's worth mentioning that an in-depth knowledge about this context, that is shear strength of soil, is also much needed uh, in the context of practical uh, geotechnical engineering applications. So far, specifically from this subject, uh, we have learned about the introduction and concept of the shear strength of soil, then followed by a Moore-Coulomb failure in analysis, different laboratory tests for determination of shear strength parameters. Now, this test include direct shear test, triaxial shear test, and unconfined compression test. Further, this triaxial shear test can be classified into one of these following categories: consolidated drain, consolidated undrained, unconsolidated undrained. So we'll discuss about each of these tests in the subsequent discussion of this presentation. Okay. And at the end of this week, we have learned stress controlled and strain control test and stress bar. So in this week, we will be trying to solve a few numerical problems pertaining to this aspect. Okay, so without much delay, we'll start solving the problems. And this is our first numerical problem. So in this problem, it has been asked that what is the shearing strength of soil along a horizontal plane at a depth of 3 meters in a deposit of sand having the following properties. Now, what are these properties? First of all, the angle of internal friction phi value is mentioned as 36 degree. Dry unit weight gamma d is given as 18 kilonewton per meter cube. Then, sorry, Question C, it's having a value of 0, so it's quite expected because the the soil formation is typically sandy in nature. The specific gravity of soil solids, GS, this is given as 2.72, and in addition to this data, we have to assume that the groundwater table is at a depth of 2 meters from the ground surface. Okay. So this is the problem statement. Depending on that, we have to answer this question, that what is the shearing strength of soil along a horizontal plane at a depth of 3 meter in this kind of deposit. Now, to address this question, we'll take the help of Moore-Coulomb failure analysis. So, as per the Moore-Coulomb failure criteria, as you know, that shear strength of a soil deposit can be defined in this fashion: C plus sigma n tan phi, where C and phi, these are the shear strength parameters of the soil, shear strength parameters, and sigma n, this is the normal stress acting perpendicular to the failure plane or plane of failure. Okay, so this is the shear strength of a soil deposit. Obviously, this is as per Moore-Coulomb failure criteria. more Coulomb failure criteria or strength theory. So therefore, if we plot this strength theory in the shear stress versus normal stress plot, so it will be something, it will look like this. So this is the angle of internal friction, and this intercept is nothing but cohesion, and this is the failure envelope. Okay, so this is tau equals to C plus sigma n tan phi. Now in this problem, as we can see that this shear strength parameters of the soil are given to us. So in terms of angle of internal friction and the cohesion. So these are the two shear strength parameters. So C value is given as 0 and phi value is given as 30, 60. Okay, so these are the shear strength parameters for the present problem. So therefore, our first job would be to determine the value of sigma n. And again, we have to be very careful about the last sentence of the problem, that we have to assume the groundwater table is at a depth of 2 meters. So therefore, while we will be determining the shear strength of this kind of soil deposit, we have to basically consider the effective normal stress in place of the total normal stress. Okay, so in terms of, if we write here this equation, this Mohr Coulomb strength equation in terms of effective stress, this equation would be C prime sigma n prime tau prime phi prime. So C prime and phi prime will basically will consider these two values only, and sigma n prime, that we have to calculate. So how? Because the location of the horizontal plane is mentioned in this problem. So if we basically draw the soil profile, so this is the ground surface, and at a depth of 3 meters, suppose here, so z equals to 3 meters, we have to calculate the shear strength. Okay, now here we have to calculate the shear strength value. Now in between this 3 meters, so at a depth of 2 meters, the groundwater table has been located. Okay, so this depth, this is 2 meters. Now our primary concern is to determine the normal stress sigma n prime. So sigma n prime we can calculate if we know the dry unit weight of this portion. So for this portion 2 meters, and for this remaining 1 meter, if we know the submerged unit weight, because this portion is under complete submergence. So this is the remaining 1 meter. So gamma D, so for 0 to minus 2 meter, your gamma D, this is mentioned as 18 kilonewton per meter cube. Okay, and minus 2 to, okay, so two meter to 3 meter, we have to determine the gamma prime. Now we'll first use the dry unit weight value to calculate the void ratio of the soil. Okay, so the void ratio of the soil, since we know gamma D equals to GS gamma W upon 1 plus C. So we can calculate the void ratio value from this equation. So it's 18, GS value is 2.72. Okay, so this is the value of GS. Gamma W we can consider as 10 kilonewton per meter cube divided by 1 plus C. So from this equation we can get the value of 1 plus C as 18 divided by 27.2, that is 0.66, 0.662, or the value of void ratio would be 1 minus 0.662, that is 0.338. Oh, sorry, I did a mistake here. So this value, this is 27.2 divided by 18, that is 1.511, and therefore the void ratio value would be simply 0.511. Now we have calculated the void ratio value to calculate the submerged unit weight only, because we know the submerged unit weight is GS minus C divided by 1 plus C gamma W. Okay, so again it's 2.72 minus 1 divided by 1 plus 0.511 into 10. So it will be 1.72 divided by 1.511 10. So that is 11.38 kilonewton per meter cube. Okay, so we have the dry unit weight for the portion 0 to 2 meter, and we have the submerged unit weight of the soil from 2 meter to 3 meter. So we can now calculate the effective normal stress as 18 multiplied by 2 plus 11.38 multiplied by 1. 36 plus 11.38, so it's 47.38 kilonewton per meter square. So therefore the tau value, it will be C prime sigma n prime tau phi prime. Now this is 0, this will be 47.38 tan of 36. So multiplied by tan of 36, so this value 34.42 kilonewton per meter square. So this is the answer. Okay, therefore when the shear strength parameters of a soil is given you can determine the shearing strength of that soil uh, along any plane if you know the normal stress which is basically acting on that plane. That is very much essential. So right now we considered a horizontal plane, so that's why the calculation of normal stress, that is nothing but the effective overburden stress, was sufficient to determine the shear strength acting on the horizontal plane. However, if the plane was not horizontal and straight, it was at some angle with the horizontal, suppose alpha, then we have to consider only the normal stress, which is basically acting perpendicular, the stress perpendicular to that plane. Okay, so the normal stress value for that case will be different. Okay, so therefore we have to be very much uh, mm, careful about the plane. So on which plane we are going to determine the shear strength of the soil. Okay, so along which plane we are trying to determine the shear strength of the soil. So I hope is it okay? It's okay from your end also. So if so, then we can take the next problem. So the next problem, so it's about a cylindrical sample of soil having cohesion of 78 kN per meter square and an angle of internal friction of 21 degree. So this cylindrical sample is subjected to a self pressure of 100 kilonewton per meter square. What is the deviator stress at failure? Okay, so what is the deviator stress at failure? Also determine the angle made by the failure plane with the major principal plane. So we'll first draw the physical planes. So this is the cylinder, cylindrical sample. Okay, this is the cylindrical sample. Now these are the stresses which are acting on this sample. So this is your sigma 1 and this is your sigma 2, sigma 3. Why? Because these planes are free from any shear stress. So that's why whatever normal stresses will act on this plane, that will be purely major principal stresses. Okay, and depending on the magnitude of the stresses, the stress, the vertical stress or the axial stress will be the major principal stress and the radial stress would be the minor principal stress. Okay, so this is from the basic mechanics. Now, as mentioned in this problem, that this is the failure plane, suppose, and this is making an angle alpha with the horizontal. We are assuming right now. Okay, so we need to figure out what is the actual magnitude of alpha considering the given inputs. Okay, so considering the laboratory conditions. Now, so this is the failure plane. So these are the physical planes. Now, if we try to draw it in terms of mode circle, so in the mode plane, mode stress plane, so this is your tau axis, this is your normal stress axis. Okay, so this is the failure envelope, and this intersect is your cohesion, and this value is your angle of internal friction. Now we can draw the state of stress in terms of a Mohr circle. Okay, so this is the center of the Mohr circle. Sorry, so this is the center of the Mohr circle, this point. Now if we, so at the failure condition, this Mohr circle will touch the Mohr failure envelope. It should touch. Now from this tangency point we can draw a plane, and this plane is nothing but your this physical plane MN. Okay, suppose this is your point A, this is your B, this is your D, this is your E, and this is your A, and this is point O. This is not required. Now this is your sigma 3, and this is your sigma 1. So please keep in mind that right now we are talking about, or we are addressing the condition of failure. Okay, so that's why Mohr circle is basically touching the failure envelope. Now we'll draw an analogy between these planes. Now what does it mean by major principal plane? So major principal plane is the plane on which the major principal stress is basically acting. Now as I have mentioned earlier, that due to the absence of initial stress acting on the radial as well as axial axis, so this will be the major principal stress principal stress directions. So the axial one is the major principal stress axis, and this radial one is the minor principal stress axis. So therefore, this horizontal plane is nothing but the major principal plane. So this is the major principal plane. Okay. Now, if we try to identify this plane in this Mohr stress circle, so we can easily identify these planes. So this AE, this is the failure plane, this is the failure plane, so this is the failure plane, and this AB, since B, so this is the sigma 1, and sigma 1 is basically acting on this plane. So this is this AB, this is the major principal plane. Okay, this is the major principal plane. Now this angle we have to calculate for this problem. And please keep in mind, whatever angle you get in the physical plane, that will be double in the case of more stress plane. Okay, so this is from the simple geometry. Now we'll first try to determine the deviator stress at failure. Now what is deviator stress? So deviator stress is nothing but the difference of major principal stress and minor principal stress. Okay, so this is the first objective of this problem, and secondly we have to determine the value of alpha. This is the second objective of this problem. So this is also, you can denote this deviator stress by sigma d. Okay, now to determine this sigma d, we should know what is the major principal stress at failure, because we know the minor principal stress at failure from the problem statement. Now what is that value? The value is nothing but 100 kilonewton per meter square, because it's mentioned in the problem that the cylindrical sample of soil is subjected to a cell pressure of 100 kilonewton per meter square. That means this value sigma 3 is 100 kilonewton per meter square. So we know the minor principal stress at failure, because this value will remain constant as per the fundamentals of triaxial test. Because in case of triaxial test, the second phase of triaxial test, the confining pressure or the cell pressure is kept constant, and only the stress in the axial direction is being increased until the state of failure occurs. So this is the phenomenon associated with the second phase of triaxial test. As we know that any triaxial test includes of two phases. So the first one is consolidation phase and the second is the shearing phase. So in the shearing phase, the confining pressure is kept constant, and only the stress in the axial direction or in the vertical direction is going on increasing until the state of failure achieves or occurs or is attained. Now this confining pressure, from this confining pressure we can easily calculate the sigma 1 value at the state of failure. How? By the concept of Mohr stress circle. So if we clearly observe the Mohr stress circle, then what is this AE? So from the Mohr stress circle, so here we can write that from Mohr stress circle, this AE, okay, first let me consider this triangle. This triangle. Okay, triangle AEF. So triangle AEF. Now from this triangle, so if this angle is phi, so this angle should also be phi. This angle should also be phi. So we can write sine phi equals to, what will be the sine phi equals to? AE upon AF. So AE often with A. Now what is AE? AE is the radius of the Mohr circle. So AE, this is the radius of the Mohr circle, and we can write this radius of the Mohr circle as sigma 1 minus sigma 3 by 2. And what is AA? AA, this is nothing but, if we can write this point as O, so this is the origin, so it's FO plus OA. So this is FO plus OA. Now this FO, so for FO we need to consider the small triangle one. Okay, so this one. So from this small triangle we know this one as cohesion intercept C. We know this is the angle phi, so FO will be C cot phi. Okay, so this is from the simple geometry. So C cot phi, because this intercept divided by this intercept, this dimension divided by this dimension will be simply tan phi, and from this equation, tan phi equation, we can calculate the OF value. This is right, I'm writing here, so this is C cot phi. Okay, so this value. And what is OA? So the value of OA is nothing but sigma 1 plus sigma 3 by 2. Sigma 1 plus sigma 3 by 2. Now if we substitute this values in this expression, that is A by AA, so first of all it will be sigma 1 minus sigma 3 by 2 divided by C cot phi plus sigma 1 plus sigma 3 by 2. Now if we simplify further, then sin phi would be sigma 1 minus sigma 3 divided by 2C cot phi plus sigma 1 plus sigma 3, and again this will be sigma 1 plus sigma 3 sin phi plus 2C cos phi equals to sigma 1 minus sigma 3. Now if we take sigma 1 as common, it will be 1 minus sin phi equals to sigma 3 sigma 3 1 plus sin phi plus 2C cos phi. Okay, so from here we can write the sigma 1 as sigma 3 1 plus sin phi by 1 minus sin phi plus 2C cos phi by 1 minus sin phi. So this is the relationship between sigma 1 and sigma 3 at the state of failure. Okay, at the failure condition. So this will be further simplified as sigma 1 equals to sigma 3 tan square 45 plus pi by 2 plus 2C tan of 45 plus pi by 2. Now if we take this tan square 45 plus pi by 2 as n phi, so if we introduce a notation for this, so this will be root n. Okay, so this is the relationship between sigma 1 and sigma 3 at failure. Okay, so where n phi is nothing but tan square of plus phi. Now, as you can see, for this problem, what are the values of phi, c, and sigma 3? So, for this problem, your sigma 3 is 100 kPa. Okay, so as mentioned, that sigma 3 is 100 kPa. Sorry, this value is 100 kPa. And what are the values for C and phi? So C is 78 and phi is 21 degrees. So your C is 78 kilonewton per meter square and phi value is 21 degree. Now if we substitute these values in this expression, so we can easily calculate the sigma 1. So sigma 1 it will be, so for this problem, first we can calculate the n phi value. So n phi would be tan of 45. So it will be tan of 45 plus 21 by 2 square. That means it's 2.12. Okay, so this is 2.12. Now this value would be 100 multiplied by 2.12 plus 2 multiplied by 78 multiplied by root under 2.12. Therefore, this will be 100 into 2.12 plus 439 into 14 kilonewton per meter square. Now, as we mentioned earlier, we have to calculate the deviator stress at failure. Okay, so all these values at failure. So it's sigma 1 minus sigma 3. So the excess vertical stress. So earlier it was all around cell pressure, sigma 3. So how much excess pressure is required to drive the failure? That is nothing but sigma 1 minus sigma 3. So sigma 1, it is the total axial stress, and sigma 3 was already there. Sigma 1 minus sigma 3. So it's sigma 1 minus sigma 3. So that means 339.14 kilonewton per meter square. So this is one of the answers. Now coming to the second part of this problem, that we have to also determine the angle made by the failure plane with the major principal plane, which is nothing but 2 alpha, as we already discussed earlier. So we have to determine the value of alpha, because alpha is the angle made by failure plane with the major principal plane in the physical plane. So we need to calculate the value of alpha. Now if we consider this triangle again, triangle AEA, so this is your 90 degree. Sorry. Okay, so this is your 90 degree. Now from the simple geometry, we can say this 2 alpha value is a summation of these two angles, that is AEF and EFA. So we can write here that this EAB, this angle EAB is a summation of angle AEA, angle AEA plus angle EAF, sorry, EFA. Okay. Now what is the value of EAB? So this is 2 alpha. What is the value of AEA? So this is 90 degree. And what is the value of EFA? So this is 5. So alpha would be 90 degree plus 5 by 2. So that means 90 degree plus 21 degree by 2, or alpha equals to 55.5 degree. So this is another answer. So this is part A and this is part B. Okay. So this is from simple geometry. So we have calculated the deviated stress at failure as 339.14 kilonewton per meter square, and the angle made by the failure plane with the major principal plane as 55.5 degree. Okay, so please cross check all the calculation, as I might be wrong in the calculation part. Okay, however, fundamentally it's okay, conceptually it's okay. Now we'll move on to our next problem, that is problem number 3. So in this problem, the results of consolidated drained and undrained triaxial test on 2 samples of normally consolidated clay are given. So this is the type of test and corresponding minor principal stress and the deviated stress at peak. Now, first of all, we have to calculate what is the difference between angle of internal friction for consolidated drain and undrained test. And secondly, we have to determine the pore pressure in the consolidated undrained test at failure. Okay. So, what we'll try to do first, we'll first recall the relationship between sigma 1 and sigma 3 at failure. Okay. So, we know that sigma 1 equals to sigma 3 n5 plus 2c, or rather we can write tan square 45 plus 5 by 2 plus 2c tan of 45 plus 5 by 2. Okay. Now we know the sigma 3 for each of this test, whether it's consolidated drained or undrained, and we know the sigma 1 minus sigma 3. So we can basically make an additional calculation here, and that is sigma 1. Now what will be the sigma 1? So sigma 1, it will be sigma 1 minus sigma 3 plus sigma 3. So therefore for the first test, drain test, it will be 300 plus, sorry, 657 plus 300, that is 957. And for the second case, it will be 252 plus 200, that is 452. Okay, so these all are in kPa. Now we have to know that for normally consolidated clay, your normally consolidated clay doesn't have any cohesion. So C value will be 0. Now if C value becomes 0, then the second part will vanish. So leaving behind sigma 1 equals to sigma 3 tan square 45 plus 5. Okay, so this is the modified relationship in between sigma n and sigma 3 for normally consolidated clay. So that we have to keep in mind. So this is only valid for normally consolidated clay. Now we'll calculate the 5 values one after another for each of these tests: consolidated drained and consolidated undrained. So first we'll calculate for consolidated drained. Okay, now can you please tell me what is the consolidated drain test and what is consolidated undrained? What is the significant difference between the two? Okay, so as I have mentioned earlier that triaxial test consists of two phases. Okay, so the first one is consolidation and the second one is shearing. Now here in both the cases and these two phases, the naming of these two phases will depend on the drainage condition, whether it's allowed or not. So for example, if the drainage valve is open throughout the test, mean in both the phases, then it will be termed as consolidated drained. So the drainage valve is open in the consolidation as well as in the shearing phase. However, if the drainage valve is open for the consolidation phase and it's not opened for the shearing phase, then it will be termed as consolidated undrained. And if it remains closed throughout the test, considering both the phases, then it will be termed as unconsolidated undrained test. So these are the three classifications of any triaxial test. Therefore, the fundamental difference between these two cases is the drainage valve is kept opened in the case of consolidated drain test throughout, means shearing and consolidation. However, for consolidated undrained test, the drainage valve is kept open for the first phase, that is consolidation, whereas in the second phase, that is shearing, it's closed. Okay, so that's why in the second test we will be having the generation of excess pore water pressure, and that we have to calculate at the state of failure as asked in this problem, also in the second part of this problem. Okay, so right now we will be concentrating on the determination of angle of internal friction considering both the test. Okay, so sigma 1, so for first test, your tan square 45 plus 5 prime by 2 is your sigma 1 prime by sigma 3 prime. So what is prime? Prime in the sense these are represented in terms of effective stress conditions. Now in case of drain test, your effective and total stresses are same. Okay, so this you can write sigma 1 by sigma 3 because the conditions are given, the test conditions are prescribed in terms of total stresses, not in terms of effective. However, for drain test both are same. Okay, so your tan 45 plus 5 prime by 2, this will be simply sigma 1 by sigma 3. And for the first case, sorry, so essentially the 5 prime value would be tan inverse sigma 1 by sigma 3 minus 45 multiplied by 2. Okay, now if we substitute the values, so for example, your sigma 1 value is 957 and the sigma 3 value is 300. 957 by 300 minus 45. So if we calculate, then 5 prime would be 31.51 degree. So this value is obtained from the consolidated drain test. Now coming to the consolidated undrained test, we can basically deduce a similar expression for the undrained friction angle. Okay, so here we are using phi u. U denotes the undrained condition. So it will be 2 times again tan inverse sigma 1 by sigma 3 minus 45. Now for this case, the values are different. Sigma 1, sigma 3 values are different. So it's 452 for sigma 1 and 200 for sigma 3. 45. Okay, so if we calculate, then the value is 22.74 degree. Therefore, the answer to the first question of this problem would be, so the difference is 5 prime minus pi u, that is 31.51 minus 22.74. How much is it? So it's 8.77 degree. Okay, so this is the answer of the first question to this problem. Now coming to the second part, determine the pore pressure in the consolidated undrained test. It's quite obvious, because in the first case we will not be having any excess pore water pressure because drainage valve is opened. So we'll have only the generation of excess pore water pressure in the second test, that is consolidated undrained test. Now, how can we determine that pore water pressure? So we can easily determine that pore water pressure by expressing the relationship between sigma 1 and sigma 3 in terms of effective stresses. Okay, so this is obviously for consolidated undrained test. So at failure, so you can write sigma 1 prime equals to sigma 3 prime tan square 45 degree plus 5 prime by 2, since your C prime value is 0, okay, for normally consolidated soil. Now again we can write that sigma 1 prime is nothing but sigma 1 minus u. Now u is nothing but the pore water pressure. And as you know that effective stress is total stress minus pore water pressure. So the major principal effective stress, the effective major principal stress would be sigma 1 minus u. Similarly, the effective minor principal stress would be sigma 3 minus u tan square 45 degree plus 5 by 2. Now, what are these values? Sigma 1, sigma 3, and 5 prime. So, sigma 1 is nothing but 452 kPa. Your sigma 3 is 200 kPa. And what's about the 5 prime? It's 31.51 degree. Okay, so please don't do any mistake regarding this phi value, because now the relationship is expressed in terms of effective stress condition. Okay, so that's why we have to consider the effective friction angle only. And since we are dealing with the same soil sample, so this value will be valid for the for this soil sample. Okay, so 31.51 degree. Now if we substitute these values in this expression, so it would be 452 minus u equals to 200 minus u multiplied by tan square 45 plus 31.51 by 2. So therefore 452 minus u, 200 minus u. Now this value would be 3.19. So therefore 3.19 u minus u equals to we are just rearranging this equation. So okay, 186 or u equals to 84.93. So this is the answer. Okay, so in this way we can also determine the pore water pressure, which is basically developed inside the soil sample in the consolidated undrained test. If we know the total stress conditions pertaining to the failure condition, and if we know the drain shear strength parameters. Okay, so please keep in mind that we should know the drain shear strength parameters, not the undrained parameters, that is phi u and cu. So if we know the drain shear strength parameters, then we can utilize this expression, this relationship between the effective major and minor principal stresses at the failure, and we can easily deduce the obtain the pore water pressure value. Okay, so these are the two parts of this problem that we have already addressed. Now we'll proceed to the next problem, that is problem 4. Now what is mentioned in this problem? So in this problem, two consolidated drain triaxial tests are performed on a cohesive soil. Now in the first test, the confining pressure is 300 kPa and failure occurs when an increase of 700 kPa of the vertical stress is applied. In the second test, the confining pressure is 400 kPa and failure occurs when an increase of 900 kPa is applied. What is the value of cohesion for this soil? So for this problem, we have to calculate the cohesion of the given soil. So how we can calculate that, we'll see through this problem, through the solution of this problem. So two CD tests are performed. So consolidated drained. That means the drainage valve is kept opened throughout both the phases, consolidation as well as shearing phases. So that's why there will be no excess pore water pressure developed inside the soil sample, and therefore your total and effective stresses would be equal. Now two conditions are talked about in this problem, that is CD1 and CD2. Now for CD1, the confining pressure was sigma 3 was 300 kPa and sigma d was 700 kPa. Whereas in CD2, your sigma 3 was 400 and sigma d 900. Now you can ask a question, why I have written sigma d instead of sigma 1? Because here it's mentioned that an increase of 700 kPa. So in excess of this 300. So earlier this 300 was acting all around the soil sample. So in the radial and in the as well as in the axial direction. So to obtain the failure or to attain the failure, we have to apply an excess or an increase of 700 kPa only in the vertical direction. So similarly for CD2, an excess or an increase of 900 kPa. So this sigma t is nothing but, as you know, that this is sigma 1 minus sigma 3. So therefore your sigma 1 would be sigma t plus sigma 3. Okay, so that means 700 plus 300 equals to 1000 kPa. And here also sigma 1 would be 900 plus 400, that is 1300 kPa. Now we will utilize the relationship between sigma 1 prime and sigma 3 prime. So sigma 1 equals to sigma 3 tan square 45 plus 5 by 2 plus 2c tan of 45 plus 5/2. Now for CD1, we can write that thousand equals to 300. So we are just substituting the values pertaining to CD1 test, consolidated drain test 1 plus 2C tan 45 plus 2. And our main target is to determine the value of C. Now coming to CD2, so this is 1300 and this is 400 tan square 45 plus 5/2 plus 2C tan of 45 plus 5/2. This is your equation 1. This is your equation 2. Now if we simply deduct equation 2 from equation 1, so this is the algebraic operation which what we are doing here. So minus 300 would be minus 100 tan square 45 plus 5/2. So this will cancel out. So what is the operation? Equation 1 minus equation 2. So therefore your tan square 45 plus 5/2 will be simply 3, or the 5 value you can calculate as 30. Okay, so this is the angle of internal friction for the given soil. So this is not needed. Okay, we have to report the question only. So therefore we can substitute this value in any of this equation. For example, from equation 1 we can write 1000 equals to 300 into 3 2C root 3, or 2 root 3C would be 1000 minus 900, that is 100, or C equals to 100 by 2 root 3, or C equals to your 28.87. Okay, so this is the answer. So we can also write that C and C prime value would be same. So instead of C and phi, we can also write, so it would be more appropriate. So if we write in terms of C prime and A prime, because prime indicates the drained condition, okay, effective in terms of effective stress parameters. Since for this test the drainage valve is open in both the phases, consolidation and as well as in the shearing phase, so there will be no excess pore water pressure developed inside the sample, and total and effective stresses would be equal. So whatever cohesion and friction angle will be getting by performing this test, that will be solely the drained parameters, drain shear strength parameters. Okay, so that's how, if we know the test conditions, or if we perform two tests on the same or identical soil sample, so we can easily calculate the shear strength parameters. Okay, so this is obviously pertaining to the case of consolidated drain. So this is the analytical approach. So also we can go for the graphical approach, where we have to plot the two mode circles corresponding to the failure state of stress obtained from CD1 and CD2. So in that following that approach also, we can determine the shear strength parameters. Okay, so if time permits, then we'll see that procedure also in the subsequent sessions. Okay, so for this time being, this is all for solving problem 4. So how to solve the problem 4 to obtain the value of cohesion for the given soil sample. Okay, so I think it's fine. Now we'll go for problem 5. So it's a big problem statement here. So first of all, a 38 millimeter diameter saturated sample is 76 millimeter high and weighs 1.58 Newton. It's tested in a triaxial compression test. Specific gravity of the soil constituents is 2.57. Sample is subjected to a confining pressure of 100 kPa without allowing any drainage to occur. The pore water pressure is measured at 74 kPa. The sample is now allowed to drain until the pore water pressure is 0, indicating that the sample has been fully consolidated. If the volume of the sample has decreased by 12%, what is the compression index Cc of the clay? So this is the first part of this problem 5. Now coming to the second part, same sample after consolidation in the triaxial cell is submitted to an undrained compression test, the confining pressure being 100 kPa. At failure, the pore pressure is 46 kPa and the load on the sample is 132 Newton, which is applied to the piston. The height of the resulting sample is 2.4 mm shorter. Assuming that during the test the sample retained the shape of a right cylinder, determine the major principal effective stresses value. Okay, so truly speaking, again this is a case for consolidated drain, because in the first part of this problem the data related to consolidation, isotropic in the sense means consolidation occurring in all directions. So that data is given. And coming to the second part, it's the shearing phase and under undrained condition. Now we'll try to answer both the questions which are framed in this problem. So in the first part, we have to calculate the compression index Cc of the clay. So therefore, we have to first know, what is the definition of compression index. So we have, I think, learned this from the previous week, that is from the chapter of consolidation, and it's nothing but the Cc value is nothing but delta E divided by log of sigma 2 prime divided by sigma 1 prime. Now, what are this sigma 1 prime, sigma 2 prime and delta E? So delta E, this is the change in void ratio, change in void ratio due to increase in effective stress, increase in effective stress from sigma 1 prime to sigma 2 prime. So if the effective stress increases from sigma 1 prime to sigma 2 prime, and for that change, if delta E amount reduction is happened in the void ratio, then we can define the compression index in this fashion, that is delta E change in void ratio divided by logarithmic of log 10 of sigma 2 prime by sigma 1 prime. So therefore our first job would be to determine or to figure out these values, delta E values, sigma 2 prime values, sigma 1 prime values. Okay, so it will be better to write here that effective confining pressure and please keep in mind that this type of consolidation is different from the odometric consolidation, because in the case of odometric consolidation, consolidation occurs only along the vertical direction. So that was or that is one dimensional consolidation. However, this is a case of isotropic consolidation where the consolidation is happening throughout all the directions. Okay. Now, first we'll try to determine the uh, unit weight of the soil sample, and why that we'll see. So, the weight of the sample, the weight of the sample is 1.58 Newton. So this is the weight. Okay. And what is the volume of the sample? The volume of the sample is pi by 4 square h. So this is your W and this is your. Since the sample is cylindrical in shape, so the volume of the sample would be pi by 4 square h. Now what is the value of D? The D value is 38 square and the value of h is 76. Okay, so these are the sample dimension into 10 to the power minus 9. So that it would be 8.62 into 10 to the power 5. So therefore, the unit weight, and obviously saturated unit weight, because the sample was tested under saturated condition. So it would be W by 1.58 Newton divided by 8.62 into 10 to the power 5 meter cube. Okay. That means 18.33 kilonewton per meter cube. Now, again we know that this gamma sat is nothing but Gs plus E divided by 1 plus C gamma. So this is 18.33. And what is the GS value for this problem? So it's 2.57. So 2.57 plus C divided by 1 plus C would be 18.33 divided by 10. Our E value we can calculate from this equation as 0.885. Okay. Now, truly speaking, this E value is the E1 corresponding to sigma 1 prime as, so before the consolidation. So before the consolidation, what are the states of stress? So this is the confining pressure 100, and this is the pore water pressure. Okay, so rather put me these values in this fashion, because otherwise this 2 and 1 will misinterpret. Okay, so 2 and 1 means intermediate and major principal stress. So rather let me put in this fashion: sigma C1, that is confining stress 1, and sigma C2. So corresponding to sigma C1 prime, so sigma C1 prime was 100 minus 24, that is 76. Oh, sorry, 100 minus 74, that is 26 kPa. And at this condition, the value of U1 was 0.885. So this is the E0 value we can say, the initial void ratio before consolidation occurs. And sigma C2 prime, this would be simply 100 minus 0, that is 100 kPa. Now we don't know the E value, but we can calculate the delta E from this equation. The delta E by 1 plus E0 equals to delta V by V. Now what is the volumetric strain for this problem? So it's 12%. Therefore delta E, it would be 1 plus E0 delta V by V, that is 1 plus 0.885 multiplied by 0.12. So 0.23. So therefore the compression index CC, this would be 0.23 divided by log of this is sigma 2 sigma 1. Okay, so this will be 100 by 26. So 0.3. So this is the answer. So in this way we can calculate the compression index from the triaxial test as well. However, this is applicable for isotopic consolidation. Okay, now we'll move forward to the second part of this problem, that is we have to determine the major principal effective stress value at failure. So coming to the second part, what we'll do first, so we'll first calculate the deviated stress, that is sigma D, and which is nothing but sigma 1 minus sigma 3, and which is again nothing but the force applied to the piston divided by the corrected area. Why this corrected area is used? Because as the sample is basically deforming with the progress of the test, the area will be modified. Okay. Further, since its undrained condition, its undrained condition, your delta V, that should be 0. There will not be any volume change. Therefore, whatever volume, so suppose this is the initial volume and this is the corrected volume, this should be 0, or V0 should be equated to Vc. Now, V0 we can write H0, H0. This is the cross-sectional area of the sample, and this is the initial height of the sample, and this is the corrected area, and this is the corrected height. So therefore, the corrected area we can write A0, H0 by Hc. Now, since axial deformation is happening, so your Hc will be modified in this fashion: H0 minus delta H. Okay. So Ac we can further rewrite as 1 minus delta H by A0, or A0 divided by epsilon A. So this is the corrected area due to axial deformation. Now, what is epsilon A? So epsilon A is the strain. Okay. Now, for the second part of this problem, as we can see, the confining pressure is 100 kPa. The port pressure at failure is 46. The port pressure at failure 46 kPa, and the load which was basically applied to the piston was 132 Newton, and the height of the resulting sample is 2.4 mm shorter. So this is the axial deformation basically happened for the soil sample. So we can summarize the values as that sigma 3 equals to 100 kPa. The force was 132 Newton. Please let me check. Yeah. And the pore water pressure U is 46 kPa, and delta H is nothing but 2.4 mm. And what was the initial thickness of the soil sample? That was 76 mm. So therefore, we can calculate the dimitric stress at failure after calculating the corrected area. So AC, so this is your A0 divided by 1 minus epsilon A. Now what is A0? A0 is pi by 4 into 38 square. So it's 1.134 into 10 to the power 4 meter square, and epsilon A, this is your delta H by H0, that is 2.4 by 76. That is 0.0316. Okay. Now if we substitute these values here, so it would be 1.134 into 10 to the power minus 3 divided by 1 minus 0.0316. So AC would be 1.171 into 10 to the power minus 3 meters square. Now once the corrected area is obtained, so we can calculate the sigma d value, that is F divided by AC. It is 132 divided by 1.171 into 10 to the power minus 3. The force is in Newton and the corrected area is in meter square. So therefore it will be 132. So 112.72 kilometer per meter square. Okay. So this is the sigma 1 minus sigma 3, that is 112.72 kPa. Now we know that sigma 1 minus sigma 3 will be equal to sigma 1 minus sigma 3 prime. Therefore here we can write sigma 1 minus sigma 3 prime, again 102.72 kPa. Now how we can write? Because we can write in this fashion, that sigma 1 prime minus sigma 3 prime is nothing but sigma 1 minus mu minus sigma 3 minus mu, that is sigma 1 minus sigma 3, because UU will be cancelled out. So therefore sigma 1 minus sigma 3 prime would be 112.72. And what is the value of sigma 3 prime for this problem? So this is sigma 3 minus mu, that is 100 minus 46, because U value is given as 46 and sigma 3 value is 100. So 54 kPa. Therefore sigma 1 would be 54 plus 112.72, which is 166.72 kPa. Okay, so this is the answer of the second part of this problem. So the major principal effective stress is 166.72. Okay, so this is the process by which you can calculate the effective principal or effective principal stresses in the undrained condition, undrained test, if you know the pore water pressure which is basically developed inside the sample. So the basic steps are as follows. So first you have to calculate the deviatoric stress, which is the force applied to the piston divided by the corrected area. Corrected area in the sense, as a sample undergoes deformation, so its area will be modified, and the modified area you can calculate from this fundamentals, that is under undrained condition the volume change will be 0. So therefore the expression of corrected area would be A0 divided by 1 minus epsilon, where A0 is the initial correct area that you know from the sample dimension, and epsilon A is nothing but the axial strain. Axial strain is your the axial deformation divided by the initial thickness of the or initial height of the sample. So you know the force applied to the piston, you know the corrected area. So if you divide the piston force to the by the correct area, so you will be having the deviated stress. Now this deviated stress would be same in terms of total and in terms of effective stresses. So if we rewrite this expression in terms of effective stresses, so you can calculate the effective major principal stress once you know the effective minor principal stress. And effective minor principal stress was the total stress minus the pore water pressure, and this pore water pressure was measured as 46 kPa under the undrained condition at failure. Okay, so and this was a very interesting problem. So from this problem we have learned how to determine the compression index. That was the first part of this problem, and in the second part we have also learned how to determine the major principal effective stress under undrained condition. Okay, given the confining pressure, the pore water pressure, the axial deformation, and the piston force. Now we'll take the next problem. So in this problem, the total horizontal and vertical stresses at a point X in a saturated sandy medium are 170 kPa and 300 kPa respectively. The static pore water pressure is 30 kPa, and at failure, the excess pore water pressure is measured to be 94.50 kPa. And the shear stresses on the vertical and horizontal planes passing through the point X are 0. And effective position is 0 kPa, and the effective angle of internal friction is 36 degree. So we have to determine the shear strength in kilopascal up to 2 decimal places at point X. Now, if we try to visualize the state of stress at point X, so suppose this is point X, this is point X. So you can see that it's acted upon by sigma 1 in the vertical direction and sigma 3 in the horizontal direction. Why? Because the shear stresses on the vertical and horizontal planes passing through the point are 0. That means these vertical and horizontal stresses are nothing but the principal stresses, and vertical is having the higher value, so it will be the major principal stress, and horizontal, this is having the lower value, so it will be the minor principal stress. Okay, so these values are, so sigma 1 value is 300 kPa and sigma 3 value is 150. Now what we have to do? We have to basically determine the shear strength at point X. Now for that, we have to first identify the failure plane. So along which plane the failure would occur. This alpha, the determination of alpha is the first job for this problem. Now how we can determine this alpha? So this alpha can be determined as 45 plus 5 prime by 2. Why? Because we have seen at the in the very beginning problem, so we have basically derived this expression, that is the failure plane inclination with respect to the major principal plane as 45 plus 5 prime by 2. So that means it is 45 plus 36 by 2, that is 63 degree. Okay, so this was the first job which we have already performed. Now the next case, we have to calculate the sigma n, and this sigma n would be the normal stress which is basically acting on this plane mn, that is on the failure plane. Now how we can calculate this sigma n? So this sigma n we can calculate by considering the concept of, or by based on the concept of stress transformation. So sigma n, which is basically acting perpendicular to mn, so this value, rather we can say sigma n prime, it will be better to with sigma n prime or sigma n. So this will be your sigma 1 prime plus sigma 3 prime by 2 plus sigma 1 prime minus sigma 3 prime by 2 cos of 2 alpha. This is considering stress transformation. Okay. And please keep in mind, we are calculating in terms of effective stresses, not total. So that's why we have to consider sigma 1 prime and sigma 3 prime. Now what will be the sigma 1 prime? So it will be sigma 1 minus u. Now what is the value of u? So the value of u is, for this case, is a summation of 30 and 94.50. Okay. So now once this sigma n prime is known, we can calculate the tau value as sigma n prime tau phi prime. Okay. Now for this problem, your C prime value is 0. So leaving behind only sigma n prime tau phi prime. Now we'll try to get the actual values. So first we'll calculate the total barometric pressure. It's 30 plus 94.50. So that is 124.50 kPa. Now sigma 1 is, sigma 1 prime is sigma 1 minus u, and sigma 1 is 300 minus 124.50. That is 175.50 kPa. Okay. And sigma 3 prime is sigma 3 minus u, that is 170 minus 124.50, which is 45.5 kPa. And the alpha value we have calculated as 63 degree. So sigma n prime would be sigma 1 prime plus sigma 3 prime by 2 plus sigma 2 cos of 2 alpha, that is 175.50 plus 45.50 by 2 plus 170.50 minus 45.50 cos of 126. So it's 72.29 kPa. Therefore, your tau value would be 72. So it's sigma n prime tan phi prime, so 72.29 multiplied by tan of 36, which is 52.52 kT. Okay, so this is the main trick uh, that we have to identify, that you have to go for that stress transformation to determine the effective normal stress acting on the failure plane. So that is very, very essential to address this question. Okay, so from the given state of stress, we can calculate the transform stress, that is the normal stress acting on the failure plane. Obviously, in terms of effective stresses, then you can utilize the Mohr-Coulomb failure criteria to calculate the shear strength on that plane. Okay, and first, the failure angle information, that what is the angle made by failure plane with the major principal plane, that is also very much important, and that we have calculated from this equation 45 plus 5 by 2, and that we have derived in one of our earlier problems in today's session. Okay, so this question was asked in a GATE examination 2018. Okay, so now if this is fine for all of you, we can take the next problem. So problem again given in 2000 GATE examination 2018. So in this problem, conventional drain triaxial compression test was conducted on a normally consolidated clay sample under an effective confining pressure of 200 kPa. The deviated stress at failure was found to be 400 kPa. An identical specimen of the same clay sample is isotropically consolidated to a confining pressure of 200 kPa and subject to standard undrained triaxial compression test. If the deviated stress at failure is 150 kPa, the pore pressure developed. So in this problem, we have to calculate the pore water pressure for the undrained case. So the same sample is basically tested under drain triaxial compression and undrained triaxial compression. So two conditions are basically prescribed in this sample. So for the first one, so this is CD. So we can see the confining pressure sigma 3 equals to sigma 3 prime is 200 kP. Okay, and the deviated stress sigma 1 minus sigma 3 prime, sigma 1 minus sigma 3, that is sigma 1 minus sigma 3 prime, that is 400 kPa. So therefore sigma 1 prime is 400 plus 200, that is 600 kPa. Now coming to the second case, that is CU, consolidated undrained, the total stress, the total confining pressure was 200 kPa, and the deviated stress sigma 1 minus sigma 3 was 150. Okay, so this is similar. This question is basically similar to one of our previous problems, and we can easily address this question. So how? First, we have to calculate the drain shear strength parameters for the soil sample, and that will utilize in the case of undrained case. Okay, by writing the relationship between sigma 1 prime and sigma 3 prime in terms of effective stress conditions. So by that way, we can easily determine the pore pressure developed inside the sample. So from this equation, from this condition, CD condition will first determine the C prime and phi prime values. Now, as you can see that the sample which was tested, that was normally consolidated clay. So for normally consolidated clay, your C prime value would be 0. Okay, cohesion would be 0. So your C prime would be 0 since this is normally consolidated. Now we can utilize this equation. Sigma 1 prime equals to sigma 3 times tan square 45 degree plus 5 by 2 prime tan of 45 plus 5 by 2. This part is your 0. So obviously I prime you can calculate from this equation tan inverse root under sigma 1 by sigma 3 prime minus 55. That will be 2 into tan inverse sigma 1 prime is 600 and sigma 3 prime is 200. So your 5 prime value would be 30. Okay. So we have obtained the drain shear strength parameters from the consolidated drain test data. Now we'll use this data for the CES. So again we can write sigma 1 prime equals to sigma 3 prime tan square 45 plus 5 prime by 2. This is for normally consolidated. Okay. Now the sigma 1 prime we can write sigma 1 minus u and sigma 3 prime sigma 3 minus u, because in this case sigma 1 prime and sigma 1 is not equal. So please keep in mind that in this case your sigma 3 prime is sigma 3 minus u. There will be a pore water pressure, excess pore water pressure, and sigma 1 prime will be sigma 1 minus u, since it's tested under unrest condition, multiplied by tan square 45 by 2. So we have basically solved a similar problem in today's session. So I will not discuss about the procedure further. So we can easily calculate the u value after substituting the values of sigma 1, sigma 3 and I prime. So your sigma 1 value is sigma 1, where you can calculate 150 plus 200, that is 350 kPa. So sigma 1 is 350, sigma 3 is 200, and 5 prime we have calculated as 30 degree. So from this we can calculate the u value as 125 kPa. Just you have to substitute. Okay, so for your better understanding, so just you have to substitute here. So 350 minus u equals to 100 minus u into 3. So therefore 350 minus u equals to 600 minus 3u, 2u would be 250, so u would be 125. Okay, so this is the okay. So now we'll end this session by taking this homework problem. So this homework problem is taken from GATE examination 2020. Now in this problem, the total stress path corresponding to different loading conditions for a soil specimen under isotropically consolidated stress state are shown below. So this is the stress path corresponding to different loading conditions. So these are the loading conditions is basically are mentioned in this table. The first one is compression loading, while sigma increasing, sigma 3 constant, sigma 1 increasing, sigma 3 constant. The second loading condition is compression unloading, sigma 1 constant, sigma 3 decreasing. The third one is extension unloading, sigma 1 is decreasing and sigma 3 is constant. And the final one is extension loading, that is sigma 1 is constant and sigma 3 is increasing. Now what we have to do, we have to basically establish a correct match between the stress paths and the listed loading conditions. Okay. Now before answering this question, we have to have a clear understanding of stress path. Now what is stress path? So can you please let me know? Okay, so already it's 6:58. We'll not solve this problem in this session. Rather, we'll take this problem as homework, and I'll request all of you to attempt this question at your home. And for any difficulties, please let me know in the next session. But we'll wind up this session by having a concept of stress path. Now, what is stress path? So stress path, it is nothing but uh, a line which connects series of points, which connects series of points. Now each of these points represent the state of stress experienced by the soil specimen soil specimen during the progress uh, so this is the stress path. Now if we draw, or if we try to have a visual inspection, so suppose this is your tau, this is your sigma n. Now this is the envelope. So as per the triaxial condition, your sigma 3 remains constant and you are increasing the sigma 1 value. Okay, sigma 1 value in this fashion. Now it will go on increasing and stop until the failure occurs. Okay, so the last Mohr circle touches the envelope, so yield envelope. Now as you can see, the state of stress is basically changing as the test progresses. Now if we pick the peak point of the Mohr stress circle, that is, the coordinate of this point is sigma 1 plus sigma 3 by 2 and sigma 1 minus sigma 3 by 2. And if we try to make a plot between these two parameters, so the line connecting these 2 points, as the test progresses, the state of stress is basically changing. So that will basically give you the stress. This is the stress path, and this is your sigma 1 minus sigma 3 by 2, and this is your sigma 2. So this is the visual illustration of the stress path. Now we'll discuss it in more details in the next session. So this is all for today's session. So I will wait for a few minutes. So if you have any doubts or you need further clarification regarding the problems which we have solved today, so you can freely ask me. Otherwise, I will end this session here. So thank you for joining this session and have a nice day. So we'll again meet on next Sunday, that is on 31st March at 5 p.m. Okay. So with this, I am ending this session here. So if you have not any doubts or if you don't require any further clarification, at least for the problems which we have solved today. Okay, thank you. Then I am ending this session here. Have a nice day. Okay.